Okay, we're going to be going over the PowerPoint for Chapter 14. That's on magnetism. And once again, this is a review. Hopefully, I can point out some questions that would be on a test, and we can see the answers to those. And hopefully, this will be a good refresher for you. And if you can think back to those lessons earlier in the year, then this should help solidify it in your mind. Okay, first we're going to look at the standards involved. They are 8.PS2.1, design and conduct investigations depicting the relationship between magnetism and electricity in electromagnets, generators, and electrical motors, emphasizing the factors that increase or diminish the electric current and the magnetic field strength. And then 8.PS2.2, conduct an investigation to provide evidence that fields exist between objects exerting forces on each other, even though the objects are not in contact. Okay, when we start talking about magnets, I think everybody knows that the magnets have two poles. They have the North Pole and the South Pole. We know Santa Claus is at the North Pole, and then at the South Pole, I'm not so sure. But we do know that opposite poles attract. When we had our magnets out and we had the one that had the N on it, and we put it against a magnet with an N on it as well, they would push away from each other. You could actually feel a force field in between the two, and they were actually repelling each other. So like poles repel. And then it's important to know that magnets are strongest at their poles. It's not at the ends. When you're taking a magnet, you don't normally stick it on the side. You stick it on the end, and that's where it'll be the strongest, whether that is at the North Pole or at the South Pole. But the magnetic field is the invisible area around a magnet, where the magnetic force is exerted. There are magnetic domains, and they are groups of atoms with their magnetic fields pointing in the same direction. And then the Earth's magnetic field is called the magnetosphere. And Earth's magnetic field is like a bar magnet, All right, when we talk about magnetic domains, I thought it would be beneficial to do a quick search of the images of magnetic domains. And if you will look, the electrons that are in a magnet are floating around freely. And if we look up here in this first one, you can tell they're kind of all going in the same in different directions. They're just very, very random about where they're aiming. And then when they actually line up in the same direction, like this image right over here, you can tell that magnet, that's going to be a magnet. These things are not always lined up, and so they are what you would call a temporary magnet. But this is what a magnetic domain is when you hear the term magnetic domain. Once again, here's another image, and if you'll notice which section is going to be magnetized and which is not. And obviously you can look right here, they're all going in random directions, but over here on the far right, you notice that they're all lined up in the same direction. And so this is what we are talking about when we talk about the magnetic domain. And then once again, I've done a Google search for the magnetosphere. A lot of you have heard about that, and that's the magnetic field around the Earth. And this is kind of a neat looking picture. This one, you can tell the Earth right here in the middle, and the magnetic field, actually the North Pole is going to be up here, the South Pole is down below. And then you see that one of the important aspects of the magnetosphere is to protect us from some of the harmful rays and radiation that come from the sun. There's sometimes solar flares and different things that come that way. And these are really buffeted by the magnetosphere. The magnetosphere during the daytime, when we're looking at the sun, you can tell it's not as high. It is really facing the impact of the radiation from the sun, so it's getting pressed around. And then if you look on the backside at nighttime, notice how the magnetosphere, it is a lot further away from Earth, so it's really stretched out farther back through there. But this magnetosphere is just very important to our survival on the Earth. And when you look at it, you can see, once again, how on the side of the sun during the daytime, it's not as far away from the Earth. It's not as thick in that area because it is doing a lot of work right there. Then at nighttime, um, the magnetosphere extends much further away. Okay, chapter 14, section 2 is talking about electromagnets. And I want you to really think a lot about electromagnet, how electricity and magnetism work together. We've talked about that when we talked about the electromagnetic spectrum, that we have electricity and magnetism work at 90-degree angles from one another. And so they're always a team. But when we built electromagnets, if you remember in class, they are any wire with a current running through it would generate a magnetic field. So when electricity is going through a wire, and that could be plugged up into an outlet, or it could be running off of a battery. Remember when we talked about the electromagnets, the things that you had to have an iron core, you had to have wire, and then you had to have some form of a battery or some type of electricity. And then that would create an electromagnet. It can be strengthened in several ways. Once again, we've done these investigations in class. You have to wrap the wire into a coil, and the more coils, the stronger it is. So if you just wrapped it around a few times, it might barely pick up a paper clip, whereas if you wrap it around a lot of different times, then it's going to make it much stronger. Also, putting an iron core inside the coil is very, very important. If you put a pencil in the middle of it, that's not going to make a difference. You're going to have something that's iron, that's going to have a lot of electrons in it, that will line up with the magnetic domain. And then another way to strengthen the electromagnet is to use a stronger or a bigger battery. And this is pretty much common sense. The more electricity that you're running through it, the stronger the magnetic field will be. Also, electromagnets are different from natural or permanent magnets in several ways. Electromagnets can be turned on and off. Natural magnets are always magnetic, and that's just a lot of common sense. We've seen those that we've used in the classroom, either the little small neodymium magnets or the other horseshoe magnets. We couldn't turn those off. Those were always going to have a field, whereas the electromagnet is going to be um, able to be turned on or off depending on if the battery was connected. And then you can change the poles of an electromagnet by flipping the battery. When you turn the battery over, then the flow is going to go the opposite direction. Natural magnets poles are permanent, and then you can control or change the strength of an electromagnet, but a natural magnet strength is not going to change. It's always going to be the same. It's important to know that motors and generators also work using the electricity and magnetism. And the electric motors are going to convert electrical energy into mechanical energy. And if you remember, you've had several questions on quizzes and on tests about this. So these are 2 points. They have a slide all their own because they are so important. So you need to really think about the differences in this. But if you have a motor, you know you have something that is turning, that is moving, that is mechanical. And for the motor to work, it's going to have to have some form of electrical energy. And that energy is going to then be turned into mechanical energy. And then an electric generator is going to be generating electricity. It's going to be making electricity. So it's going to have to turn something, and that's going to be mechanical. So turning mechanical energy into electrical energy is an electric generator. A lot of times you have people use windmills or they can use water flow, and that is turning something mechanical. And then that would in turn produce the electrical energy. A lot of you may have a generator at your house that you put gas in, but the gas has the motor that is going to turn something, once again, mechanical energy, energy of movement, into electrical energy. And then finally, we're going to watch a short, about a 2-minute YouTube video about motors and generators. The presenter is a little bit hard to understand. You really have to pay attention to him. But this video really shows you the differences in the motors and the generators. So let's pay attention to that one really good.
Two of the most important applications of the relationship between electricity and magnetism are the electric motor and the electric generator. By definition, an electric generator is a device that converts mechanical energy into electrical energy using electromagnetic induction. The reverse conversion of electrical energy into mechanical energy is done by an electric motor.
This is a very simple and basic structure of an electric motor. We can see the battery, the commutator, the brushes, the copper wire loop, and the permanent magnet. The brushes are attached to a wooden support, and the commutator is fixed to the loop of copper wire. The commutator rotates freely, rubbing against the brushes. Now, when we pass current through the circuit, this creates a magnetic field around the wire, which interacts with the field of the permanent magnet to produce a rotation of the loop that looks like this. The electric motor and the electric generator are related like two sides of a coin. In general, the task of an electric motor is to convert electrical current into mechanical force. On the other hand, an electrical generator converts mechanical force into electrical current. So as you can see, we can simply rearrange our motor into a generator. In this case, we will provide the mechanical force with a windmill rotor attached to the loop and connect a bulb in place of the battery. We will leave the magnetic field as it is, and as the wind rotates the blade, an electrical current is produced.
One thing to remember is that you can generate an electric current by running a magnet in and out of a wire coil. You may have remembered that we use the slinky to kind of show like the wire being in a coil, and then if you had like a magnet, like a bar magnet, as long as you can let it interact with the wire, the magnet going through it back and forth, that would create an electrical current. And that was what they were doing in the video when they were turning that part around with a magnetic field. They were doing the same thing in reverse. Well, I hope that this has been enlightening to you. Hopefully this has refreshed your memory some on it. And I will see you on the next video. And as always, stay safe.